One way to improve a language model is to train it with more data. Another way is to have it produce more tokens per answer. This is because by producing more output tokens per answer, you give more opportunity for the model to explore and critique its answers. In part 1 of this series, I explained how, via chain of thought, you can have an LLM generate longer answers. In part 2, I'll explain how to improve performance by generating multiple answers in parallel and having a verifier pick the best of those answers. By the end of this video, you'll have a sense of the different approaches for sampling and verifying and understand what works and what doesn't. As I outlined in part 1, we're looking here at the difference between using training compute, so you can improve a model by training it some more, and the idea there is to get it more familiar with the underlying patterns, hopefully patterns that capture what you need to answer questions at real-time inference. But the other approach, which until maybe the last few years has been underappreciated, is to increase test compute, which means rather than spending effort on training the model some more, instead spending effort on having the model produce more tokens per answer, which can be done in series via longer answers, or can be done in parallel that we'll talk about today. Now, I laid out a map here of the techniques for exploring and critiquing answers. And on the one side, you have pure sampling approaches, and on the other side, you have pure critique approaches. And you need both because you need to create more answers, and then you need to decide which ones you want to keep. And some of these approaches, like chain of thought, for example, they kind of combine the two. A chain of thought will allow you to kind of explore the answer in a linear fashion and include critique within it if the model is trained to provide that kind of critique. So in that last video, which I recommend looking at as a precursor, you can check out how chain of thought is introduced. You can understand the significant improvement it provides in terms of final answer quality. And you can also understand some of the techniques used for sampling that around temperature, top P, top K, min P, and beam search. And just as a brief recap on that, for single shot solutions, so where you're generating one solution, the key takeaways are that using low temperature and or beam search will tend to give the best results. Using top P or min P or less so top K will help you avoid bad tokens. So while doing a small amount of sampling is good, you do want to avoid very rare tokens that can completely throw your answer off kilter. And then last of all, using chain of thought results in very significant improvements in performance. Although I'll give one caveat here that most models now are trained very heavily using train of thought type responses. And so it's not entirely necessary to prompt the model to use chain of thought. You can play around with it. In certain cases, it can still give improvement, but a lot of models are now trained, so they'll automatically just give chain of thought when you ask any question. So for today's video, we're going to focus on parallel generation of answers rather than just series. And we're going to talk a lot about using verifiers, because if you generate a family of answers, that's not good enough. You need to know which one is actually the best answer so that you can provide that final answer. And that's not a trivial thought or a trivial thing to do, but it's something we're going to cover today. So the way I'll talk through verifiers is, first of all, I'll describe how we're going to generate a family of answers, in other words, sampling. Then I'll go through a few verification methods. So calculation, voting, scoring. I'll talk a bit about process versus output verification. And then as usual, I'll go through some notebook examples where I look at the performance. If you do parallel sampling, I'll look at the performance assuming you had a perfect verifier. In other words, you can pick out the best answer given, say, 8 parallel answers or more. Then I'll go through a voting-based approach and a scoring-based approach, and I'll show you the results I got when running those on GSM-8K, which is grade school maths. And last of all, I don't usually do this, but I think it's instructive to cover a few of the papers. I definitely am missing a lot, but I'll show you 1 or 2 key papers around verifiers and the different approaches that they have and the success they achieve for different classes of problems. So to start off, let's take a look at how to sample. And we're going to take a fairly simple approach. I think it's a good approach though. We're going to use a temperature of 1. Using a temperature of 1, you might recall from the first video, means that we're going to sample the probabilities of the next token according to what the language model predicts. So normally a language model will predict a distribution of tokens. If we set the temperature to 0, we'll automatically pick the most likely token. If we set it to 1, we're going to sample according to that distribution the language model provides. Now, you could use higher temperature. Some papers, they'll recommend using 1.6, 1.7. But I did run some ablations on that, and I actually found performance can deteriorate sometimes. So I'm going to stick with 1, but probably you could use a bit higher. The second thing around sampling is we're going to use a top P of 0.9. This means that we're only going to consider tokens that add up to 0.9. So if the top 3 tokens are 0.5 and 0.4, we're only going to consider the top 2. If they're 0.4, 0.3, and 0.2, they all add to 0.9, we'll consider the top 3. So this is how top P works. You only consider the tokens adding up to that probability. Alternatively, you could use min P, which means only consider tokens with a minimum probability of 0.1. That will work fine as well. In some of my ablations, I got better performance with top P, so I'm using that, but I'm not saying in general that's going to be a better approach. What I think is better is using either top P of 0.9 or min P of 0.1 rather than using min K of 20, which will take just the top 20. The problem with that is if the 20th one's extremely unlikely, it could end up being a very bad token that throws the answer off kilter. So I think top K is probably a bit less robust, so I recommend using top P or min P. Now, just a side note here, you can use beam search. Beam search will generally give fairly good answers, although it takes more compute because you're literally sampling a few in parallel and then picking the highest probability full sequence. But this is good if you want to generate one answer. It's less good if you want to generate multiple answers. At least in some of the tests I ran, when I run beam search, it'll take, say, the 4 most likely answers, but they often are very similar. And that's not what we want here. We want the answers to be quite different. We don't want them to be so different that some of the different ones are just rubbish, but we do want them to be significantly different so we actually get a range of answers, and hopefully the right one is somewhere in there. So once we've got a body of samples, and it could be small, like 1, 2, 4, 8, could be huge, like, something like 512, we need to figure out which one is going to be the best answer. And that brings us to verifiers. So there are a few classes of verifiers, and I'm probably leaving some out too, but the most desirable is if you can just calculate once you've generated a solution whether it's correct or not. And this, of course, only happens in limited problem classes. If you're doing certain coding problems or certain maths problems, it is some of those problems, you can run them through a checker and you will know straight away if it's right or wrong. And this is beautiful because you know for sure once you hit the right answer, and you can just stop generating more samples. So the only question really, if you're in this class of problem where you can calculate or check the answer, the only question is how efficiently you can sample, i.e. how good are the different generations you make? Are they just way too wild where none of them have a chance of being good? Or are they way too narrow where they all just resemble each other and you're never getting out of that wrong patch of wrong answers into a region where there's a correct answer? So this is, this is the most beautiful one. Another approach then is voting. So here we're talking more subjective. We're talking about answers that are not exactly right or wrong, at least as per a checker. And we can use a voting type approach. Now you could do this with humans. You literally ask them to vote between A, B, C, D, E, etc. Or you could ask a language model to vote A, B, C, D, E. This is something that I will show you in the notebook. And the benefit of doing voting is that it's a side-by-side comparison. So you're saying, all right, is this answer good relative to this answer? Because you're asking them to either be ranked or to pick out the best one. And often it can be easier to make a relative judgment than it can be to make an absolute judgment. So for that reason, voting, in theory, for some problems, it can be better. A drawback of that is if you ask a human or an LLM to vote on the best of 512 answers, that's a lot of information to parse through. And so it becomes hard to pick out the best answer among a very large number of options. Now you can think of cascading things kind of in a fractal way where you just compare them in 4s and then you whittle down until you get to the end of the pyramid with 1. And maybe that helps out a little bit. But in principle, the benefit of voting is it's a relative decision rather than absolute. The drawback is that it's a bit harder to scale. And when I say harder to scale, I mean it's a bit harder to scale versus a scoring approach. This is where you take answers A, B, C, D, E, and you get a human or an LLM to independently give a score, say 1 to 10 for each of them, and then you just rank each of the answers by score and you take the top one. So the benefit here is it's fairly easily scalable. The drawback is it can be hard to calibrate a score in absolute terms. So if you show an answer to some reasoning problem and you ask a human or LLM to give it a score 1 to 10, yeah, you can provide a rubric around aspects of a good answer or not, but it can be sometimes hard to establish really what an 8 is. Like, what does an 8 fundamentally mean, especially when you go across different classes of problem. Now, just a side note here that applies for all verification except for the calculation approach. Better sampling can hurt verification. So when you create more samples, yes, it's good, you've better chance of hitting the right answer, but you're also going to generate a lot of bad or spurious answers. And if those answers happen to be kind of misleading or they kind of look good, but they're not good, this can incline to reduce the performance of a verifier. So it's not a complete and easy win. When you create more samples, it can make things harder to pick out the best sample. And so even though you might have the best answer within your samples, it becomes really hard to find which one is actually the correct one. Just a few more notes, of 2 more slides on verifiers. So you can improve a verifier if you decide to do a voting or a scoring type of verifier. And there are 2 broad ways I'll describe here of doing that. One is fine tuning. So quite simply, you would generate some answers, some samples, and presumably you know in advance which one is the ground truth. And then you can train a verifier to get better on picking out which is the correct answer. And why does this work? So why would you not just train the base model that's generating the answer in the first place? Well, the idea is that verification is somewhat orthogonal to solving. So there's a certain skill of solving, and verifying is a little bit easier because when you see a solution, it's kind of easier to tell if it's correct than to generate it in the first place. And so if you believe that those 2 skills are at least partly orthogonal or partly a different skill set, then you can come up with a justification for why you might fine-tune a verifier as well as fine-tune the base model and get to better performance than fine-tuning the base model alone. The other way you can improve a verifier is by just optimizing the prompting. For example, you can provide multi-shot examples. We will do this. Or you can use a stronger language model to prepare the prompt and hopefully structure it in a way so that you give guidance around scoring. For example, you might say, if there's any mathematical inconsistency, then you can't score it more than 4. So by improving the prompt, you can improve the quality of the verifier. Now, something we won't do in the example, but is mentioned a lot in literature, is this idea of output versus process verification. If you're generating an answer, you can generate that answer in a series of steps. Chain of thought will often do it in a series of steps, but you could even specify the number of steps, like 3 different steps. And now in principle, if you have steps towards the solution, you can grade not just based on the final answer, but also based on the individual steps. And it turns out that this seems to improve performance by verifying each of the steps. So yeah, we're not going to do it, but in principle, it seems that you get better results by having verifiers at each stage rather than just on the final answer. Now, often it's not possible to verify deterministically the steps, even if you have a coding problem where the final answer can be checked. That doesn't mean you're going to be able to deterministically check the previous steps. Although in that case, one approach taken is you can roll forward an intermediate step. So if you've got step 2, you can just roll forward some different temperatures and see if any of them actually hit a correct answer that is verifiable. And based on the percentage of correct answers from roll forwards, you could then assign a grade to that second step. So that's kind of a Monte Carlo type approach that you could use to verify the intermediate steps. And of course, you can use human or LLM scoring for the intermediate steps. So that's another type of approach. Yeah, I've already said here, process-based verification tends to outperform output. But yeah, it's complicated. I would say everything in this video is complicated, and often you think things are doing better, but you didn't run enough samples, or there's something else happening in the background. Like, for example, you have a lot of hard questions in your data set, and suddenly you hit some easier questions, and the easier questions do better with more sampling, but the harder questions don't. So I'll talk a bit about that more with the papers. But generally, you have to be very, I think, skeptical of approaches that are going to improve performance because there are so many factors that affect how well verifiers perform. Just some other techniques here I'll mention. If you have generated a lot of samples, you can use majority voting. So you can simply pick out the answer that appears the most often. This tends to work. This works with easier problems. Majority voting is often sufficient. You can imagine if you were generating, say, 10 samples and 6 of them give the same answer, then majority voting kind of works well. But as you get to very hard problems where you have to sample, say, 100 and you only see 3 correct answers out of 100, then majority voting tends to break down when the correct answers are in a very small minority of the total samples. So yeah, generally you'll see across papers, majority voting is kind of a baseline you can compare any other verifier approach to, but it kind of struggles when you get to really hard problems. Then there's Monte Carlo. Monte Carlo is a way to decide how you should sample. It's useful in particular for multi-step problems because it will help you decide how much you should explore some new steps versus just keep sampling older steps that work well. So Monte Carlo can be more efficient than random sampling, although it's kind of complicated building up a Monte Carlo setup. You can take a look at my video on that if you're interested. And yeah, I'd also mention that whether you use Monte Carlo or you use a tree search type algorithm or just random search, they are all subject to having a good verifier. If you don't have a good way to verify the final output or the process steps, if that's what you're doing, then it doesn't really matter what kind of search you're going to do. It's not going to be effective at finding the right final answers. So with that, we will take a look at how this looks in a notebook. And I'm going to compare a baseline. Then I'll look at producing different numbers of samples. And then I'll look at voting-based and scoring-based approaches. So I'll be working out of the advanced inference repository. Here I've got a folder now that is called sampling. And I've reorganized this. So in part 1, you have my notebooks here that are looking at chain of thought and also the effects of different temperatures, top P, top K, min P, and beam search. And then in part 2, I've got this notebook here, which is on sampling with verifiers. So this is the notebook we want. You can access all of these notebooks by going to trelis.com/advanced inference, and you'll find a wide variety of scripts covering everything from API calls, speed tests, citations, redacting personal information when you're submitting requests to, say, OpenAI. That's the Monte Carlo, so you'll find the Monte Carlo folder there. A series on security, fact-checking. Okay, I won't go through it all. So let's get started with the notebook we want, which is on verifiers. And to do that, I'm going to deploy an A40 in RunPod. And if you want to find this template, you can go to one-click LLMs and you can just search for fine-tuning. You can click then on this template here, or if you want to find one for vLLM, it's available right here. Sorry, for Vast AI, I meant. You can find one there. Okay, so I've selected that template. I'm going to pick an A40 and I'll deploy that pod. And when the pod is up and running, I'll upload a copy of the notebook. And I've just given it about 30 seconds or a minute, and the Jupyter lab should be ready here in RunPod. And I'm going to upload that notebook. So I'll click here, upload. And then within the sampling folder in part 2, I'm going to select the verifiers and just upload that document there. Now in the notebook, I'm going to install vLLM and datasets. vLLM is what we're going to use. We're going to use it within the notebook to make batches of queries to help speed things up. Now, there is the ability to use guided decoding. This is where you specify the structure that the language model is going to produce, for example, JSON or brackets, maybe an array. This is very useful if you want to build a judge, for example, because you get back an exact format and it's very easy to pull out the data you need from the response, as opposed from having to guess with regex or regex, which might not be systematically enforced. Now, vLLM has just recently supported guided decoding for what they call offline, which means, say, within a notebook or on your own computer without setting up a server endpoint. But it's only available in the latest version. which is not, it's not actually being deployed as part of the PyPy package. So what you need to do is install vLLM and then clone the repo and copy the files over. So this is a bit hacky, but this works for now if you want to get the latest version of vLLM. Now I need an API key because I'm going to use OpenAI's GPT-4o Mini as a judge for answering the questions. So I'm going to input that. All right, so everything has been copied and vLLM is installed. And now I've got my API key entered and I'm going to load the data set. So for this, we're going to load the GSM8K. Sorry, my font is a bit small. Let's increase that up here. Okay. And yeah, I have run this on a sample size of 32 and I run it 5 times so I can measure the variance I get between runs, because you get significant variance when you're using sampling. And then you want to know if you get, say, 80% right, you want to know if that's 80% plus or minus 5% or plus or minus 1%. But for the purpose of me demoing now, I'm just going to use one row of data so that we can print out some more information and also not have it take forever when we want to run. So what I've done is I've got this data set loaded and I'm loading just the first row in this case. I also have the option to load this, what I'm calling dataset train. And I load that from the end of the data set just to make sure it doesn't overlap with what is going to be my evaluation set here. And the reason I have this train data set is when I want to do prompt optimization, I can use my training set and then I can use my eval set to determine performance. If you do prompt optimization and you use the same data set, you're kind of just overfitting. So it's a bit of cheating. So that's why you have to use a training data set, a separate set, if you want to optimize the prompt in a somewhat, fair, independent way. Okay, so let's print out the data set, and that failed because I didn't run this set here. So it's going to download the data set and then we can take a look at some of the questions. So you saw this in the first video, Natalia sold some clips. There's the question, this is the question, then there's the answer. The answer actually has a full explanation. And then it has this quadruple hash followed by 72, which is the final numeric correct answer. So this is the ground truth, the question and the ground truth. Now I'll enable Hugging Face Hub Transfer for fast download. And I'm going to load now the Llama model. Now, differently to the previous video, I'm going to load a 1 billion parameter model, which is smaller, it's worse quality, so it's more challenging for it to get these answers correct. So you'll see the percentage correct will be lower. But I wanted to do that because already the 3B model is getting like over 80%. And I felt that if I used a worse model and made it more challenging, I would be able to see some differences. I think it's fine if you run the 3B. You may find some different patterns, but it's just quicker to run 1B. So that's what I decided to do. So here I'm loading the model with vLLM. You can see LLM here is imported from vLLM, and we then generate a few different answers to these just continuation prompts. They're not questions. I'm just getting it to continue these prompts to make sure that the LLM is properly loaded. Notice how I can feed in the prompts as a batch. You can also feed in a batch of messages, which we'll do later, and it will decode in parallel. So this is good because normally anytime you see somebody run a Jupyter notebook or a Colab notebook or a Kaggle notebook, they're probably just generating one answer at a time, which is a really inefficient way to use a GPU because a GPU can parallel process. So you will get a lot higher throughput if you can use batching. And the way to do that is, one way to do it is using vLLM. So here we have the completions. So hello, my name is Emily and I'm a huge fan of your work. All right, thanks, Emily. Now, we're going to move on to answering some of the questions in the data set. So I'm going to skip through the step-by-step part here because it's all covered in part 1 and move right away to a simple prediction where I do not use any induced chain of thought. Now the model will itself use some chain of thought, which is good and improves the answer very significantly, but I'm not going to force it to follow a chain of thought type of structure. I'm not going to use guided decoding, so I'm not going to force it to obey a certain output format. And I'm just going to do single shot. So this is my single shot baseline. So let's run this. We're going to run it. I'll go through the code in a second, but we're going to run it with a temperature of 0.25. So low temperature. We don't want it to be 0 because we know based on the last video, you do better by having just a tiny positive temperature. And I'm going to have top P of 0.9 to avoid hitting any very rare tokens that will throw the answer off. And then last of all, I will run I'll run the whole thing 5 times so we can calculate a variance in the responses. Now, actually, I'm only going to run it once here because I just want to show what everything looks like. So let's go back and quickly walk through this baseline example of running just a single shot. I'm going to turn do print to true so we can have a look at some of the stuff that's happening. You can see here I load an OpenAI client. I'm going to use OpenAI for judging. When we're judging, we're going to have the judge, which is GPT-4, provide a reason and provide a Boolean to say whether the answer provided by our LLM is correct or not. So we have next a function for evaluating the model, and the evaluation will work by iterating through each of the rows for the question, assembling that into a batch of questions. We'll process multiple questions at once to improve the speed and submit those questions for answering by the LLM in chat format. And quite simply, we're going to just submit the question. We're not going to submit a submit system message. We're not going to submit any request to do chain of thought. We're just submitting the question and we're going to get back an answer. Now, you'll notice the way vLLM works is it takes in sampling parameters when you call llm.chat. So it takes in the messages and the sample parameters. And the sampling parameters include temperature, top P, but it also includes the max number of tokens. So yeah, that's going to generate a series of outputs. We will grab the predicted answer from the outputs, and that will then ultimately get sent into the judging function, which takes in the question, the gold answer or the ground truth, the predicted answer, and it will then judge whether the predicted matches the ground truth or not. Now, as one difference to the previous script, I decided to just not provide the question. I decided just to provide the judge with the correct answer and the ground truth and decide whether it's correct based on that. I found if you add the question, sometimes it can cause the judge to try and solve the problem for itself, which is not what you want because then it might be wrong. So I just wanted to focus on here's the right answer, here's another answer. Do we have a match or not? Notice that when I get the judge to judge, I give a temperature of 0 to minimize scoring variance. Probably 0.25 would be fine as well. And I pass in a response format. This is how you do structure generation with OpenAI. You pass in a response format and you can see scoring result. That's what I talked about up here. It's forcing OpenAI to provide a reason and then a true or false on whether it's correct or not. So then we have basically what you can think of as the main function. And what the main function does is it reruns everything 5 times by default, although I'll specify 1 below for the quick demo. And it's going to iterate through for each of these M runs and run the evaluation. And then at the end, it's going to calculate the mean that we got correct across all the runs and the mean absolute deviation, which is, yeah, you can think of like variance. So we'll set that up and we'll run once here and see what we get out. Okay, so we have a ground truth answer of 72 and we have a predicted answer that is also 72. So the total correct here is 1. And yeah, because we've only run once, there's just a total correct of 1. And there's no variance because we only ran it once. So that's our simple baseline. And we can see how that performs. And I'll show you the results later on. But you can see here if we run for 8 questions, this is not 32, so it's not as statistically important. But when we ran 8 questions, this baseline was getting 75% here. So next we're going to move on and we're going to look at doing sampling where we generate multiple answers in parallel. And so we're going to look at simple sampling where we just control how many samples there are. And we will check every one of those. So if we generate 4, we will check if any of one of those 4 are correct. If one is correct, we will consider that the model got that right. So this is called pass at 4. If you generated 8 and you assume a perfect verifier and it gets one of the 8 and it gets it correct, that would be your pass at 8, pass at 16, pass at 1000. That just means how many samples you need to generate in order to get at least one correct answer within your sampling pool. So you can see this is an optimistic assumption because in practice, it's not good enough to generate samples. You need to also identify which one is correct. And that's where we're going to need a verifier to come into play. So here we have simple sampling. And just to walk through it here, the function is now a little bit different for when we iterate through the rows. I'm no longer batching the questions together. I'm just going to have one forward pass for each question. But now when I do the forward pass, I'm going to generate multiple predictions for that same question. Now, it's not immediately apparent how that works. We have to look at the sampling parameters. And when we dig into the sampling parameters, there's this new parameter I'm passing in here, n, and ngen is the number of samples I'm going to get the model to produce. And I also need to specify best of, which is here. So if I set best of and ngen to 4, that means it's going to create 4 parallel samples, and it will pick the best 4 of those based on probabilities, which means all 4 of them, and it will return 4 answers. And when we have those 4 answers, we're going to just iterate through those outputs. So here are the outputs, and we'll iterate through the outputs to grab the response for each of the parallel samples generated. And you can see by controlling ngen and best of, I can do 4 samples, I can do 8, I can do 16, I can do 32. I probably can't do more than 32 because it's going to run out of VRAM. In principle, I would have to run 2 batches then if I want to do 64, for example. But yeah, you can see how this is an efficient way to generate a lot of samples in parallel. Now, the judging is all the exact same. The question setup is the same. I'm just passing in a question. I'm not doing any fancy chain of thought setup. I'm not doing any system message. And yeah, you can see I'm doing the same validation using GPT-4o Mini. And we're iterating through each of the runs, calculating the means at the end. So let's set this up. We've got our data set of just 1. You can see, I think previously I ran with 4 samples or 4 runs. 4 samples, so 4 parallel samples. I did 5 runs and I did 32 rows of data. And in that case, I got 83% with this approach. So that will just show you what I got earlier. But just for now, let's take a look if I turn on do print. So I'm going to set that to true. And let's just run with 1 pass through. So you can see here we have the predictions. It's an array, and that array contains 4 different answers. So do you see that? Here's 1 answer. Here's another answer. Here's another answer. And here's the last answer. So you can see there are 4 parallel answers produced, and the mean total correct is 1. So that means at least one of these answers is correct. And when I look at it here, they all actually say 72. So it's getting all of those correct. Now, if you had a question that's more difficult, you might see one of them is correct, but one of them is not correct. So that's our approach here when we're doing sampling, and it's called the best of approach, and it should outperform because it can't do any worse than the baseline in principle, because it's got more samples. So the last approach, or rather the 2 last approaches, or maybe 3, I think I'm going to show you 3 verifiers, is where we have to not just produce samples, but also pick out the right sample from it. So I'm going to show you voting, and then I'm going to show you a scoring approach. So for voting, what we're going to do here is package the correct answers called verify and vote. So we're going to take the candidates, those, let's say 4, we'll enumerate them so they have a number. We'll join all the answers together, and we're going to set up another LLM, which by the way will be our Llama 3.1 1B model or 3.2 1B model. So we're still using the same small model for doing the verification as we did for generation. And we're going to get it to comment on a series of answers, provide a reason for which one is best, and then provide a vote for the candidate it wants to vote for. So here, you can see we have a system message. You're a verifier. Your task is to evaluate the following candidate answers. For each answer, identify logical or candidate mistakes, and provide a justification, and provide your answer in the following format. And notice the format here is the regex that we've specified here for the verifier. Now we're also going to enforce that regex. So we're going to enforce via vLLM the returning of a reason followed by the voting or the candidates that are being voted for. And you can see that within the sampling parameters. So let's take a look at the sampling parameters, which should be up here. So temperature. So let's take a look at those sampling parameters. And yeah, for the verifier, we have got the guided decoding argument being passed along with guided decoding params, which is imported from vLLM, and we're passing in the regular expression here of verifier regex. So yeah, you can now run with guided decoding in vLLM within a notebook, including if you're running batches. And yeah, just as another minor note here, we're actually going to do the voting as well in parallel. So we will run this voting a total of 8 times actually. And then we will take, out of those 8 votes, we will sum up all of the votes across the 8 voters and use that as our measure. So we're effectively kind of sampling across voting as well, which adds hopefully an extra layer of robustness. Now, where is 8 coming from? Well, if we're doing 4 original answers, I just have decided that I wanted to increase the amount of voters to try and improve the ability to get quality of answers. I just wanted more sampling of voters. So I'm doing twice. So if I have 4 answers, I'm going to do 8 voters. If I have 16 answers, I'm going to do 32 voters. Now you can see if we start increasing the number of answers, the voting is going to be across like a very large number, say 16 or 32, and you probably see degradation of performance there. So here I'm just running 4 samples, and there are going to be 8 different judges that are going to vote on those 4 answers. So let's take a quick look at the main loop. We're going to iterate through for each of the runs, run the simple evaluation with voting. And when we get to the voting, we generate answers using this simple evaluate model with voting. And we then verify and vote. And when we verify and vote, what's happening is we're going to run in batch mode. We're going to run 8 different voters, and we're going to get the votes for all the candidates. So the key line here where all of the votes are being aggregated across the judges is this one. So the votes, you can see here, we're incrementing according to whether or not the judge gave that candidate a vote or not. So this allows us to build up a number of votes for each of the candidates, and then we select the one that has the number of votes. And if there's a tie between 2, then we just at random pick one of the candidates that has the most votes. So we can run this now, and I'll run it quickly with m equals 1. Let me just turn on the printing so we can see some more information. So here we have some predictions. This is predictions for this question here. It's the same question for Natalia. And you can see we have the same 4 predictions. And this is still running because we're now running the voting. And by the way, in vLLM, currently using guided decoding slows down generation by about a factor of 4. It's a known issue, and it'll probably be fixed hopefully soon. So there is a drawback for using guided decoding right now with vLLM. There's not a drawback with OpenAI. It'll run pretty much the same speed. I haven't done an exact ablation, but I didn't notice any slowdown. Okay, so you can see here, the verifier is voting. Here we've got the 8 responses, voting for 1, voting for 1, voting for 2. And actually here you can see that this is not good. We should actually have reasoning be outputted from the verifier here. And so that suggests to me that there is an issue with how we are running that. And yeah, you can see that we are then aggregating up the number of votes. So candidate 1 got 5, candidate 2 got 3. So yeah, that makes sense. 1, 2, 3, 1, 2, 3, 4, 5, it adds up to 8. And so we then pick candidate 1 as the final answer. And based on that, we get 1 correct. So you can see here, a shortcoming in my setup is that the reason here is being just provided as a number, whereas we actually wanted to reason because that effectively gives chain of thought like behavior that should improve performance. So this is a good opportunity for me to show you how I would iterate through this. So first of all, I would check that my regular expression is correct. So here, I just want to check that the reason, in particular this part here, what is the regex? Let's increase my font size. What is the regex enforcing for a reason? Is it a string or a number? So I just want to check that the regex isn't accidentally enforcing a number. It's a string, so that's good. Now I'm going to take my verify and float function, and I'm going to ask it to add some one shot. I have this verifier function. Let's add in a one shot example to improve performance. And I'm actually going to say, just give me the updated messages. So I don't want it to give me the whole code. Okay. It's a pretty naive example. That's fine. So actually, let's make that 2 shots and include one example where the answer is correct and the other where it's incorrect. So I'm providing a positive and negative example as part of my few shot. And yeah, in principle, this may or may not help. But well, it should help. It should help because it's going to avoid the reason just being given as a number, which is definitely not what we want. So let's go back and put this in to the messages here. All right. Okay, and let's see how this goes. So it should take longer because we're going to provide these longer reasons. And it's also going to take up a lot of space probably. Okay. So yeah, you can see candidate 1, it thinks is incorrect. And it's still voting for candidate 1. So that's not what we want. So now I'm going to go back. Clearly it's not performing well. You help improve my verification voting function. Now, of course, it's a 1 billion parameter model, so I don't know how much you can expect. Well, let's see. It wants to add parsing checks, which I don't know if that really makes sense. This is something that ChatGPT recommends often. It will try and do parsing checks on the actual response. So you'll see here, it's actually trying to extract the reason and say there's a redundant or repeated reasoning detected. So I'm going to just go with this, but you would need to systematically look through this and check whether it's actually improving performance. But anyway, it's cheap for us to do here now. Okay. So you can see there are a few things here. First of all, clearly it's not recognizing that the answer is correct, even when it is correct. Like 48 plus 24 is indeed 72. So yeah, the model is just weak at the 1 billion parameter level. And yeah, that's going to be a problem for using a verifier. And if you do go to the 3 billion parameter model, you'll see the verifier is just better. So you won't necessarily see the same performance at the 3 and the 1 billion parameter model. It's just hard to predict as you move towards different scales of model how the verifiers perform. The other thing is I haven't checked the code, I just pasted in, but clearly this is not making sense because the number of votes is now 15 and the number of votes has to sum up to 8. So there's some logical inconsistency that's been introduced there. Either way, I have run this previously with my more naive simple prompt, which has shortcomings, but I do have some results from that anyway, I'll show later on. So the next 2 types of verifier I'm going to show are around scoring. I'll quickly show you one where we score the answers on 1 to 10, and then I'll show you one where we just binary score as being either true, correct, or false, incorrect. So for the scoring, it's kind of similar to what we do for the voting, except for every sample I generate, I just have one dedicated judge that will assign a score. I'm not averaging across multiple judges for one given score, which you could argue is shortcoming. Just for every sample, I'm using one judge. So that means if I generate 4 answers, I'm going to have 4 more responses that are going to serve as judges. So that means for every 4 samples, or for every n samples, I'm going to need 2n time responses. Whereas in the voting approach, for every n time responses, I had 3n because I did 2n for the number of judges. So yeah, this is slightly more efficient in terms of compute, but it's not sampling many judges for a given answer, which is going to probably reduce performance. So arguably, if you added more judges here for a given score, you might be able to improve performance further. Okay, so the way I set this up, the confidence verifier, is I ask for a reason, then I ask for a confidence score from 1 to 10. I provide 2-shot examples, positive and negative. You're a verifier, you're going to evaluate the correctness, respond in this format. And I did do this earlier and I checked through it more systematically. So hopefully now when we set do print to true, and we just run this on one example here, hopefully we'll see some more meaningful answers. Again, we have the 4 predictions, NGen equals 4, best of equals 4. And here you can see the verification for candidate 1. So you're a verifier. Here are the 2-shot examples, positive and negative. Find the number of clips sold. So yeah, I'm just printing out here the prompts. They're all going to look the same. And once we move past that, you can see we have the mean total correct as 1. So it's actually finding the correct answer. I mean, I found the last time too, just because for this question, all of the samples are generally correct. But you can see the confidence scores. So here are the confidence scores. So verifier response for candidate 1. The reason the candidate incorrectly assumes here, and then its confidence is 2. And then we've verifier for candidate 2, which is the answer is 72. And its confidence is 7. So yeah, it's saying the reasoning is flawed even though the answer is correct. And then here for candidate 3, it's saying its confidence is high, but there's some kind of shortcoming. So yeah, basically the 1 billion model is not all that strong. But you can see that the reasoning, it is actually giving reasoning because I gave it some 2-shot examples. And yeah, we'll see this actually does very slightly improve performance, even though it looks pretty poor here. Now, the last approach before I get to show you the results is the binary classifier. And in the binary case, it's very similar. I think I give 2-shot examples. Yeah, I give a positive and negative example. But the regular expression here is just to say an answer is either correct or it's not. And then we have one judge for every answer. And the first answer we get where the answer is deemed to be correct, we take that. So yeah, this is just binary classification. And so when I run this code snippet here, just for m equals 1, I've got my 4 predictions, which for this easy question, it gets right in all of the cases. And then we have the verifier response, and you can see the verifier is marking the first one as true, the next one is false, false, and then true. So clearly the verifier is not, at least based on just a sample of 4, we can't tell if it's any better than random. But it is formatting following the syntax we expect. And then it's taking the first true answer, and because it picks that, it's getting the answer correct for this question. So yeah, I've run all of these, and just to emphasize that the amount of data you run on is really important. As you can tell here, we're trying to get really small differences. Like even if the verifier is correct maybe 60% of the time, that's going to improve performance overall on the process. And you're just not going to be able to measure that by running one run on a total of 1 sample. So you need to greatly increase your sample size. And that indeed is what I did. So we'll move to take a look at those results now. And so here we have the results, and I'm going to show you the results for the Llama 3.2 1B model. And I will put up the results for the 3B model after the video. You'll see them linked in the slides if you want to take a look. So here we have the single shot. We have performance somewhere around just above 50% of the answers are correct with single shot. That's at a temperature of 0.25 and a top P of 0.9. And when we allow for 4 samples and assume a perfect verifier, we get significantly better performance. So we're able to find an example within even those 4 over 60% of the time, almost 70% of the time. And you can see here the error bars because I do every set of 32 5 times. Then we move to voting. So here we're sampling 4 times and trying to vote on the one that's correct. And this is basically within the error of the single shot. So we're not seeing any performance really here. Then if we do sampling, this time using scoring of 1 to 10, there's maybe a marginal improvement, but it's basically within the error of the single shot. So our verifier is not performing well. And last of all here, we have the binary scoring, and this is also not statistically improving upon the single shot approach. Now, for any of these approaches here, you should never be getting worse than the single shot approach unless your verifier is anti-correlated. In other words, it is accurately picking out the worst examples. And if that was the case, you could just flip the verifier on its head and you would statistically be able to improve. So yeah, you should never see these sampling plus voting examples get any worse than the baseline one here. But as you can see, there's room for improvement on these verifiers. They definitely could do better because we're finding a correct answer significantly more if we are using sampling than single shot. Now, I will put up the 3 billion results. What I can say is that as you move to the 3 billion size model, the verifier does improve relatively. That's not necessarily guaranteed it would, but it does improve. And we're able to get, I think, just barely statistically better when we go to a sampling approach, say with voting, compared to the single shot as we move to a larger model. Just one other note, I've only looked at sampling 4 times here. If you increase the samples, you will get improved performance. I did a quick ablation where I did 4, 8, 16, and what you see is you get a log linear plot. So you will get, if you say 2x the number of samples, you'll move up linearly as you keep 2xing the number of samples along the percentage accuracy. So you certainly could improve the performance here. Now, as we discussed earlier, whether that improves given your voting verifier or your sampling based or your scoring verifier is another question. It's very hard to predict some of the dynamics here because there are a lot of factors that influence the performance, not just of the sampling, but of the verifiers. So actually, to illustrate some of those nuanced points, I'm going to just quickly take a look at some of the papers that I went through in advance of preparing this video. One paper to look at is this one here by OpenAI. It includes a number of people you might recognize. Here's Jan Leike, John Schulman. I think they've both left. Ilya has left as well, but some well-known researchers here. And one of the key plots is this one here. So you have the number of solutions attempted per problem, and then the problem solved. And these are maths problems. You can see this majority voting baseline here. And then you can see in blue, outcome supervised. So this is where they are training a verifier based on human labeled data. So they actually run simulations, get humans to grade them, and then train a verifier. They train a verifier based just on the outputs, which, and when they use that, they get the blue results. And when they train it to be able to verify each process step, they get better results here in orange. So this is in line with what I said earlier, that if you have a step-by-step process and you use a verifier at each step, you can get better overall performance. I don't know if that's completely general, but it's in quite a few papers. There's this paper here on large language monkeys. It's a paper from Stanford, Google DeepMind, and Oxford. And one of the graphs I'll show you here is also on GSM-8K. So let's take a look. You can see if you have a low number of samples with Llama 3.8b, you're getting performance just in about the 70s, mid 70s. And actually with Llama 3, or even, with Llama 3, we're able to get that performance. It's a distilled model from 8K. And with Llama 1b, we're able to get that if we allow for a perfect verifier and sampling. But what you can see here in blue is the pass at K. This is like what I showed. It's allowing you to increase more samples, including assuming a perfect verifier. And you'll see the blue line basically gets up to 100, so you can get 100% of the samples correct. You can also get 100% correct on a maths benchmark, which is more difficult than GSM-8K. But what you also see is that it's very hard to approach the pass at N by using verifiers. So in this case here, they're using a reward model. I think it's an off-the-shelf reward model, and they're using it either in combination with majority vote or not. And you can see you're basically struggling to try and reach the top optimistic line of a perfect verifier. And that's kind of in line with the results I showed too. It's just hard to have a verifier that performs very well. Another paper here, this one talks about the effect of easy versus hard problems. And maybe actually I better start with this paper here, which is from DeepMind as well in Berkeley. And in this paper, splits up questions according to whether they're easy and hard. And it highlights that you have different verifier performance on easy versus hard problems, as you might expect. But basically applying these kind of recursive approaches, one approach here is just to iteratively revise a question. This is not a parallel sampling approach. It's just where you have a sample and you try and iteratively improve it. And what it shows is that on easier questions or medium questions, you get a better improvement percentage if you do iterative revisions versus on harder questions. And this graph here shows you using a process verifier, you can get significant improvements. This is with parallel sampling on easy questions, but you basically don't get improvement then on harder questions. And because a test set will contain easy and hard questions, this means that you can get pretty hard to predict patterns, or the patterns you get may not be representing what you think. This is well shown in this paper here, where it will show how the performance varies with the number of samples for a simple voting approach in red. I'll talk about filter vote then. But you can get non-monotonic behavior whereby increasing sampling will initially improve performance, but then it will disimprove performance. If you're using majority vote, for example, you just have too many samples and the correct answers are too small a percentage. And then here in the filter vote, a verifier is being used first to filter before then doing a majority vote. And you can also get performance that degrades initially and then improves later on. So the reason I'm showing this is just to highlight how nuanced it is as to how these verifiers perform. It's very case specific, and it's hard to say a lot of things in general that are going to be true. The last paper I'll show is this train of thought paper, which is from Google, Princeton, Google and Princeton. And it looks at 3 specific toy problems, which are quite fun. So it's got Game of 24, which is about coming up with 4 numbers that together with multiplication, division, addition, and subtraction can give you the number 24. It has creative writing, where it provides the end of sentences and asks the LLM to fill in the start of the sentence. And then it will get GPT-4o, I think, a judge to grade it on 0 to 10. And then it has a crossword problem where you have to iteratively fill in a word and keep filling in the crossword. And it uses what's called train of thought, which is where you break it into steps. And at each step, you might either ask for voting on which is the best. If you take the first step and do it 4 times in parallel, you'll then do a voting stage where you vote which step is the best, or which version of the first step is the best to continue into the second step. You can also do scoring. So I think scoring is maybe used in creative writing. And then in the crosswords approach, there's a form of backtracking, because you can actually verify if this fits. Like if a horizontal fits against a vertical and it doesn't fit, then you can say, well, that's definitely wrong, so we'll backtrack and try something else. And in all of these cases here, just by using the language model for doing voting or for doing scoring, in these 2 cases, a performance improvement is shown. So here you can see in a baseline, just with a simple input-output prompt, it's getting 7.3% in Game of 24. If you allow for iterative refinement, it's getting 27. And then if you allow for tree of thought, where you have 5 beams, and I think you're doing voting at each stage, you can get up to 74. So you can significantly improve the performance there. And then in creative writing, the scoring, just in simple input-output, you can say score here is about 38.7. And then if you include train of thought, it's getting up to 78. And in the crosswords puzzle, which when you do this tree of thought approach where you can step back if there's an answer that doesn't fit, you're also able to improve performance. Let's see if that is listed here. Sorry, no, this was table tree for the crosswords. I was wrong about that. The results for the creative writing. The creative writing results are here. So you can see that if you just do simple input-output, you're scoring somewhere around 6.5. Whereas if you have train of thought, you're scoring up more towards 8. And that's it for part 2 of 2 on this series about test time compute. If you want to find the scripts, you can go to trelis.com, trelis.com/advanced-inference. I've also put some links below to the papers I mentioned. if you want to review some of the fundamental theory for yourself. In the meantime, let me know of any questions below in the comments. And yeah, I'll add the 3 billion results into the slides, which you can click on in the description if you're interested in seeing those. Cheers.